Hello, my name is Bruce Tobey, and I want to thank Cole Publishing for giving us the opportunity to get together today so I can share with you analysis we have done on life cycle cost analysis. I said we, who is we? This presentation is based on a paper that I did in collaboration with two partners, one of whom is Bevan Baudet, PE, who is known to many in the water and wastewater industry for his long distinguished service as the executive director of the Palm Beach County, Florida utility system, and as well from his service as a past president of the American Water Works Association. And our other partner was Scott Harder, also a PE, but Scott has made his mark as a consultant on the financial side of water and wastewater utility operations, with a particular expertise in rate setting. Together, we conducted this analysis and wrote a paper entitled Life Cycle Cost Analysis for Decision-Making and Collection System Rehabilitation. What I bring to this is my experience. I call myself a triple threat. I'm a lawyer, I have an MBA, and I've got a ton of experience in government, both as an elected official and working in those other capacities as a staff person in utility operations, for example, as a senior attorney on the Boston Harbor cleanup for the Massachusetts Water Resources Authority some years ago. The three of us all had experience in decision-making and witnessing decision-making as capital projects were planned. And it became readily apparent to us that folks needed to be reminded that valuation of the cost of a project was a critical component in making the decision on how to get a collection system or any wastewater or water utility component project accomplished. We found very often that utility managers were caught in a world of low bid paralysis, and that there was a whole new world to be shared by putting light again on the notion of life cycle cost analysis. So let's deal with the first question. What is a life cycle cost analysis? Well, it's a tool that can be used to help make sound decisions when you're weighing alternative approaches to getting a capital project accomplished. It needs to look not just at the upfront cost of getting the job accomplished, but the combination of the capital and the operating costs that will be incurred over the long term of the project's activity. In other words, how long is this project going to be up and running? 10 years, 20 years, 50 years? That needs to be considered, and the cost to be incurred over whatever period is the right period built into your analysis, not just the cost up front, but those subsequent costs. And with that data run through a proper analytical mill, what are you going to have? You're going to have the basis for a supportable business case decisions. And in the final analysis, whether you're public sector or private sector, these are business decisions. You do see a fair amount of life cycle cost analysis use in the larger components of wastewater or water utility, a treatment plant, a pump station projects, but it's equally applicable to collection system projects. It's there's another driver here besides wanting to do the right thing from a business point of view, it's legal, and that is captured by the citation in my last bullet, section 602B13 of the Clean Water Act. What that section says is an LCC must be conducted and drive the decision when state revolving loan funds are used to finance a project. Now, I fully understand that's just a part, sometimes a small part, depending where you're operating, of the funding source for a project's accomplishment. But it's there, it's not always being adhered to when SRF monies are involved, and it's going to cause problems in the long run. And I get on a soapbox on this but I do it for a reason. I've been an owner. When I was the mayor of Gloucester, Massachusetts, I was its city manager. And I was a guy who knew too much and got very involved in the intricacies of our compliance with a federal court consent decree on upgrading our collection system, indeed expanding it substantially, and how we were going to pay for it. And I quickly learned you had to do it right the first time. I'm going to say that more than once in this presentation. And a big part of that was making sure you protected your ratepayers. But another part of it was reflected in this blurb I've just put up on the screen in front of you. When the owner of the utility, be it a mayor or a general manager or an executive director, the chair of a board, when a mayor or one of those other owner representatives signs a documentation where the money is borrowed to pay for the project and it's SRF money, you're going to see a clause like the one that's up here from another area where I've done some work, Binghamton, New York, and had occasion to review all their loan documents. I don't like to read slides, but I'm going to read this one. The recipient has studied and evaluated the cost and effectiveness of the processes, materials, techniques, and technologies for carrying out the project. And to the maximum extent practicable, the project will maximize the potential for efficient water use, reuse, recapture and conservation, and energy conservation, taking into account the cost of constructing the project, the cost of operating and maintaining the project over the life of the project, and the cost of replacing the project. Now, that's not just a statement, that's a covenant. That's a binding obligation. If you violate the terms of one of these loans, they're coming back on you one way or another. They, your lender. They can call the debt. They can penalize you on the interest rates, which are often very favorable depending on where you are for SRF borrowing. And there is nothing worse than having to go back out to market and explain, first of all, to your ratepayers how that covenant got messed up. So you want to do it right the first time, and you want to be sure that that life cycle cost analysis, which is going to be increasingly used as the model for good decision making for financing purposes, is adhered to. Now, we all know the reality. There's one big devil of a challenge that anyone in the water and wastewater field is dealing with. We're going to focus on sewer laterals in this case. Those were the facts we dealt with. 800,000 miles of public sewers, 500,000 miles of private laterals. That's a whole lot of collection system, and a big part of it not in public control. In the collection system setting, there's all kinds of risk of structural failure, blockages, and overflow. And we're all familiar with the research that's shown that as types of materials to construct collection system changed over the decades, so too did their lifespans, and more failure is converging on the here and now, no matter what kind of components we use to build that collection system in the first place. With all those issues, the state of our collection system, the D+ says SCE, and that's $51 billion in collection system rehab needed in the next 25 years. So that's why we've got to get it right the first time, because these budgets for repair and replacement are limited, and you just can't afford to get it wrong and have to do it again. Find the sustainable approach, the low-cost approach in the long run, and you're going to be a winner for your ratepayers and for the integrity and sustainability of your utility in the long run. And that's why, one way or another, there's plenty of good reason for you, whether you're an owner, a manager, someone in the trenches, a financier, an attorney, anyone with an engagement wants to say hello to the life cycle cost analysis and embrace it. I trust you all are available with ASTM, which is one of the world's leading standards drafters. It works on a consensus basis with expertise in any given subject matter area being required to participate in its committees. ASTM works on a consensus basis. And there are a number of committees that deal with everything from the safety of baby clothing to jet engines and everything in between. That includes, for example, collection system standards. And by the way, it also includes the process of defining how a life cycle analysis should be accomplished so that it captures the present value of all relevant costs for installation, operation, maintenance, for a range of project alternatives over a specified period of time. And then you've got that business tool, that business decision tool, in a way that's defined by experts as being reliable to in turn rely upon in your decision making. Bear in mind the last point, broadly speaking, of the ASTM standard for life cycle conduct, a life cycle analysis being conducted, and that is when you pick your alternatives, they've got to be independent of one another and mutually exclusive of one another. The costs, well, in a way, they're pretty predictable. That upfront cost, the installation cost for the capital work to be done. Then you look to the material service life, the approach that's employed. Will it last 5, 10, 20, 50 years? There are then an array of costs that come into play. And again, we're talking about sewer laterals. So I'm going to start speaking with a little bit more specificity now to relevant costs in that sector. The main concern or primary concern in dealing with the rehabilitation of collection systems is to remove inflow and infiltration. So you can thereby minimize flows and minimize the cost of treatment by not treating water that's clean in the first place. That's operating costs, to lose the cost of treatment of extraneous water. Then there's maintenance costs to consider. To what extent during the life of the asset as improved by your project will, despite the project having been done, maintenance efforts nevertheless having to be undertaken over the course of time? And at what point is maintenance not enough and rehab or replacement required that will give rise to new capital costs? And then there's one potential credit, terminal value, salvage value, which means if your project is going to last 50 years, but the lifetime of the asset is 100, well, at the end, there will be a credit because it will only have depreciated halfway over the term of the analysis that you're conducting. Where would you look to find this kind of data? Well, as industry professionals, you're going to have a jump start on it to begin with. But on top of that, job site reports, published papers, studies. Manufactured product data is going to give you a whole array of considerations to weigh. And then last but not least is local experience with alternatives, and indeed to some extent others' experience with alternatives. But one of the things that life cycle cost analysis is meant to minimize is the kinds of anecdotal accounts that salesmen will make when they drop in on you as an owner or a decision maker in the operation of your utility. It's not about the stories, it's about the data, and you can't lose sight of that. So I put it on the slide, but it's really the least of the considerations. So what's the case study about? We focused on rehabilitating a gravity sewer lateral. It's not a pressure system, it's a gravity sewer lateral with good old gravity in a sloping pipe, carrying it from a house through the lateral to the main in the street in front of the house. We looked at 3 independent, mutually exclusive alternatives, and we analyzed them closely, and you'll see some of the data that we used in a little bit. The first was to do nothing. Just it's leaking, but maybe we can live with it, and we aren't going to do anything right now. We'll just let it be. The second 2 each refer to CIPP lining, but in very different ways, hence they're mutually exclusive. As you probably know, CIPP lining, cured in place pipe lining, is increasingly in use, as one of the many trenchless technologies employed to repair and rehabilitate underground assets without having to do cut and dig with all the turmoil that accomplishes. I knew that firsthand in Gloucester, Massachusetts, which is constant rising and falling hills, which are made of granite. And to put a new collection system into that required blasting akin to the Battle of Verdun. Therefore, I gained a first-hand approach using pipe bursting, using old water mains to include a pressurized line, and then simultaneously replace those frankly inadequate old water mains with new ones. So we killed a bunch of birds with one stone, and yet created lasting infrastructure. The difference lies in what you do to create the seal that will ensure that II stops getting into the new pipe you've created. Because here's what it's all about. CIPP puts a new pipe into the ground by unfurling with some pretty nifty machinery, but I don't want to go too deep or into areas where I may not be as expert as I think. But trenchlessly, taking a rolled up liner measured to the shape and length of the portion of lateral to be lined, and using pressure, unfurls it, unrolls it up into the lateral. It's soaked in resin. Steam or some other curing heat source is introduced, and it hardens hard as a new pipe, because that's what it is. And it's shaped and molded to the host pipe that is the old leaking lateral pipe. But there are issues, and we'll talk about those in a few minutes, challenges to the effectiveness of that approach that requires the use of some sort of sealing mechanism between the new pipe and the old. And just for a sneak preview, for example, when you look at the image to the right of this slide, you'll see at the very top of that insert, using a cutaway of the pipe to show what's going on in there when this new pipe system has been installed trenchlessly using CIPP technology. At the very top, you'll see there are two black rings. Well, those are examples of the second CIPP choice, the third bullet, pre-engineered hydrophilic molded rubber gaskets. They comply with ASTM F3240, which is the only ASTM spec for these kinds of hydrophilic components to be used in this environment, and installed pursuant to ASTM F2561, which is the only industry standard for the installation of a lateral liner that exists as well. But that brings us to the second one, second bullet, first CIPP option, which is all about, instead of using a pre-engineered molded hydrophilic gasket, creating by using an adhesive paste, a seal, having applied the paste to the tube, to the liner before it's installed. So those are the three alternatives we looked at: do nothing, CIPP with adhesive-based seal, and CIPP with the molded gaskets. So what were the costs we looked to? As we've discussed, the installation cost up front of getting the project done, to the extent that periodic replacements required, what's that cost? Projecting the longevity of the approach, how much leakage will come in, it might increase over time, by how much. So you can figure out the cost of conveying and treating that leakage. To what extent do you have to do periodic maintenance of the lateral using CCTV installation? Do you have to clean it? Do you have to grout it? And then looking at, again, case studies, experience, recent bids, what are the various cost estimates that you could be looking to for each of those considerations. Now, one thing on the molded hydrophilic rubber seals, there's been a lot of testing of these because there's a fair amount of discussion in the field as to whether the adhesive or the rubber seals have the most longevity, how and why. Testing has shown that the molded rubber seals, well, they're activated when water gets to them. Whether you use the paste or use the molded seals, the gaskets, the irony is what you're trying to get rid of, is your friend, because that water hits the hydrophilic paste or the hydrophilic gasket, and it causes it to swell. And that swelling brings the seal to close the gap, and the water can't get in. But when it stops raining or groundwater levels subside, it's going to contract, right? Because the water's gone. But then it's going to get wet again. So it's going to hydrate, it's going to dehydrate in cycles. What's going to happen to its effectiveness over time? This chart shows that the molded hydrophilic rubber seals on a third-party lab basis continue to do the job over a period of many years. An adhesive, the same kind of testing was done based on 30-day immersions to see when activated and kept wet, what do? How much water will they take in, and how much swelling will they have? Bottom line shows the adhesive-based seals. There's a limit to how much swelling those will do. They'll basically double, maxing out a little above doubling, and holding it but starting to taper off at that 35th day. Whereas the hydrophilic molded components, those gaskets dramatically inflate, and they hold it above 800% swelling, a substantial volume change, and again, sustainable. Why do we care? Why do we care about the swelling? Why do we care about the extent of the swelling? Well, you've got multiple challenges by way of shrinkage and creep that make that space between the old pipe and the new pipe, the annular space, it's a variable. It's going to grow over time. It's going to increase. Shrinkage is natural with these resins, 7 to 10% by volume. I know folks in this industry refer to the fact that the very best day in the life of a liner is its first day. Well, that's because of this kind of shrinkage that will occur. So one thing you've got to be sure of is as resin shrink occurs to that extent, your seal is going to have and hold the capacity to do the swelling that's needed to seal that space, that annular space between the hose pipe and the CIPP. The second challenge is creep. So you've got pipe underground, and it is not a static environment. It is not a stable environment. Cars will drive over these pipes if the lateral's in a driveway. The ground shifts naturally just because the planet's not particularly static. There are a whole array of factors that give rise to creep, and it can have dramatic impacts on what's going on between that hose pipe and that CIPP liner. So again, and this is, I'm told, somewhat exaggerated to make the graphic show what's up, but the scales are appropriate. And this one focuses on creep. 8 years after installation, you are looking at a degree. If you look to the molded gasket sealing mechanism on the left-hand panel, but the right hand of it, you'll see a white space between the hose pipe and the light blue CIPP. That's the amount of creep in both models there, both caulk sealing mechanism and molded gasket. But because of those limitations of the adhesive to just double in size, the yellow as it were, in the left-hand example, there's white, and that's open annular space. That means 8 years after installation, leakage has resumed in a clock system setting. Why? Well, it's an imperfect system, is what's suggested. This is manually applied rings of caulking, that, it's gunnable. So you just sort of load it on and you load the liner onto a launcher that then installs it. There's smearing that diminishes it, doesn't create a perfect ring. And then it has the limited capacity to swell that we spoke of. The molded gaskets, on the other hand, with their 800% plus swelling capability, are more than able to fill that gap. But when you go to the right-hand side, and this one, experts in the field have found quite astonishing. Well, with all the movement that creep causes, the annular space is quite large with the caulk sealing mechanism. I mean, at that point, you're beyond failure of the solution that was installed 95 years earlier. But moreover, when you look at the molded gasket, that capacity, it's like the ever-ready bunny. It still keeps on going. So there's a dramatic difference in creep management as a result of which technology you choose. So when you use the LCCC calculation method of the ASTM standard, what you're going to do is apply two equations. This is why we had Scott, and I'm not going to go too deep because my MBA only carries me so far. But basically, what you've got to do is figure out you have to determine the inflated costs of all the activities that have to occur during that period of years that you've identified for conducting your analysis. And then secondly, you have to use a second equation to determine net present value. And that would simply be the matter of discounting, using an appropriate discount rate, capturing an appropriate inflation rate, so that you identify the amount of money you'd have needed up front to fund all that has to happen, including installation, during the period of your analysis. In our analysis, we assumed an annual inflation rate of 2.25% and a discount rate of 5%. And as I mentioned earlier, the salvage rate wouldn't be irrelevant to this, but we note it nonetheless because we see these assets lasting 50 years. Hence, we used a 50-year period for a collection system. Now, we are not going to go through each of these lines, but I will tell you categorically that you will see there are three tables here. Each option is captured. The no action alternative is the first. The CIPP liner with the adhesive paste approach is second. And the CIPP with molded rubber gaskets is the third. I will take you through the upfront cost. Obviously, doing nothing, well, the installation cost is zero. But then we had to account for the II conveyancing and treatment costs, that third column, the cost of periodic inspections and remediation that would have to occur, which we assumed was grouting. We had that at 5-year intervals for the first 20 years. And frankly, at that point, the consensus was you'd give up. And we looked to a number of utilities to get their then relevant costs on II conveyancing and treatment costs, as well as the cost of inspection and grouting. And if you drop way down to the lower right corner, you'll see that the present value of all the costs we incurred over a 50-year period were roughly $9,500 per lateral, $9,500 per lateral. You go to the second case, your average installation cost is going to be $1,290. You're going to have some II, but not nearly as dramatic as in the case of no action. You're going to have 10-year inspection and grouting episodes at the first interval, and then 2 more 20-year intervals, years 30 and 50. And we tried to keep this conservative so that we wouldn't load costs on any of these. But one thing that was clear was that line would need to be replaced at 20-year intervals. And with inflation, the estimates you can see were nearly $2,000 at year 20 and just over $3,000 at year 40. Net present value, the amount of money to be set aside today, would be about $6,200. $1,290 to install, $6,200 for its life. Then you get to the CIPP with the astm 3240 compliance seals. The installation cost, well, there you go. There's the problem. $2,440 cost up front. You're buying more with the gaskets, but there's a more weighty installation cost up front. But look at the II costs. Minimal throughout the whole life of 50 years. The inspections, what they are, at 10-year intervals, low cost, with the resulting expectation, given the great success of the seals to do what they're supposed to do, no replacement in the course of those 50 years. So the $2,440 costs for installation, plus those interim costs over 50 years on a net present value basis, are just under $3,200. So you take all this data, you boil it down, you bring it into the owner, the board of directors, the city council, city manager, God forbid a mayor, guy like me. And here's what you see, that on a net present value basis, the most expensive option, based on both NPV, which is on the left, and that chart shows the unadjusted costs. So either way you slice it, the result's the same. Do nothing costs the most on an NPV basis, $9,500 upfront. Adhesive paste-based liner, just under $6,200. And the irony, because of effectiveness, the third option, the F3240 compliant liners, are the best value on an NPV basis and on an uninflated basis at just under $3,200. Dramatic differences, with the most expensive being just overwhelmed by the additional increases in costs that arise when all the lifetime costs are built in and accounted for. This is an important tool, and this case study, I think, shows why. I'm sure there are instances where the results will be different, but nothing like a dramatic case to show the value of an analytical approach. So what did we conclude? Well, in the immediate instance of this particular kind of activity, rehabilitating sewer laterals trenchlessly, the most expensive and initial installation is the least cost alternative over the period of analysis by a factor of 2. As a result, you could safely say the LCC analysis method demonstrates very clearly to the owner over the long term that the most cost-effective alternative is for the utility, and in the final analysis, those to whom a fiduciary duty is owed, the ratepayers who are paying for it. The result is you've got an analytical tool in the LCC analysis that gives a clear-cut, data-supportable business case for decision-making. It led the 3 of us in our study to have a very strong and compelling belief, indeed a zealous need to proselytize for the use of the LCC analysis in decision-making when it comes time to consider collection system work and in all regards of water and wastewater capital planning. I would say I'd have time for questions, but as the folks at Cole have explained, there's an online means for providing questions to us. And I look forward to your questions and providing answers, which are totally posted and will be available. I can run, but I can't hide. My email is btobey, B-T-O-B-E-Y, at pldolaw.com. Drop me a line. Look forward to your feedback and providing answers to questions, no matter how we get them. Again, thank you for your time. Thank you to Cole. Thank you to Bevan and Scott for their collaboration that enabled this presentation. I hope you found it useful. Have a great rest of the day.